Hey everybody, today we're going to work through, you can see the title at the top, Sketching Quadratic Functions from Vertex Form. So what I want to walk through is a method, okay, just a method to go through and sketch your parabolas. This is not a mandatory method, and I'm not even going to argue this is the best method always, but it is a method that allows us to get down a formal sketch for a parabola. In order to do that, we got to talk a little bit about some transformations, and then I want to take you through one main method, and I'll kind of slide another method in towards the end. Okay? Take a look at the first problem that you see on the screen. I want you to describe all transformations, okay? All the transformations that we are going to do to our base function. And you can see again the equation of that base function. There is your y equals x squared. So we've spent some time talking about transformations. I want you to give this one a shot on your own. Don't worry if there's a lot of hesitation. I would expect there to be. I want you to give it a shot. Let's pause the video now. Okay, we're back. So for us to examine all the transformations, we have to look at all the things that are affecting the equation of x squared. I've got this 2 out on the front. I've got this 3 on the inside, and I've got this 4 on the end. So if I took it in its parts, that 2 on the outside is going to cause a vertical, because it's on the outside of my squared, a vertical, and because it's attached by multiply, there's my stretch. We found that that 2 does a vertical stretch, and then my formal statement is by a factor of 2. That tells my reader that I'm taking all of my y values and I'm making them double what they used to be. What does that now do to its shape? It's going to make it steeper. Anytime that we make a change to our shape, we have to describe the change to slope. Okay, now I've got the -3 on the inside. I just had to erase that for a second so I could see whether that was a plus or a minus in there. The -3 on the inside. Well, since I'm subtracting 3 from all my x's, then all my x's have to be 3 bigger than what they used to be. So that means that I'm going to shift my graph because I am adding or subtracting that 3. And since it's happening to my x, that is, it's happening inside my brackets before my squared, I need to shift it horizontally. Do not tell me shift horizontally and now describe direction. We should all be good that because I have a -3 there, my 3's have to be bigger, I have to shift it to the right. But if you write shift horizontally right, then that's redundant. Like it's not needed. As soon as I have to describe right, which I have to include, horizontally becomes unneeded. It's a waste of time. So don't write that. Instead, recognize that it's a shift horizontal. We write that it's been shifted right, so we shift it right 3 units. Okay, we jump to the purple. You see that -4 on the end. Well, we should be good that that is an add or subtract, so it's another shift. Don't feel like you have to put another bullet down to then say shift. You've already described a shift in the blue. Just keep it going. So you are shifting it right 3 units. And now we recognize that the 4 is on the outside, so that's affecting it vertically. So that means I need to shift it down 4 units. Same thing. Don't write shift vertically down. Okay, if we don't get why that's redundant, try at some point to shift vertically right. And you should be very confused. As soon as you say shift vertically, it means up or down. So as soon as you say down, that means vertically. There you go. Okay, if you give me those 2 bullet points referencing those 3 transformations, then you are good. Okay, I want to try 2 more, and now that we've walked through those, I think you're going to be so much better to try them on your own. Okay, you take a look at problem B and C. I'm going to ask you to tackle both at the same time. Don't start to go part way. Just do them both at the same time, even if there's a lot of hesitancy. Okay, I want you to give both of those a shot. Pause the video now. Okay, we're back. So what I want to do is I just want to confirm your statements and we'll have a quick little discussion. What you see on the screen now are your transformations for both. Please make sure that your red statements are before your blue ones. That is, my reflection is found because it's connected by multiply. My reflection or stretch are found because they're connected by multiply. My add and subtract create my shifts. Add and add create my shifts. Those are connected by add or subtract. I hope you recognize bed mass is required. So I must do my reflections or my stretches before my shifts. Now, if you take a look at part C, it does not matter which one of these statements comes first, because both reflections and vertical stretches are attached by multiply. It doesn't matter what order I multiply in bed mass, so it doesn't matter which one of those transformations I do. As long as I'm doing my shifts in the end, then I'll have my correct transformations. Okay, there we go. Can I please just have one more little comment about that red? Please don't ever tell me that you have a vertical stretch by a negative factor. Don't. If you tell me that you're doing a vertical stretch by a factor of negative 2/3, then you've missed a transformation. If I ask you to state transformations, I need to see all of them, which means you have to make sure that you state that reflection. Okay, hopefully we matched up okay, and you were good on both. And that gives us a little bit more confidence in interpreting and writing transformations. Okay, what I want to do is I want to spend the rest of our time today sketching these functions. As I said, I'm going to add another one in on the end. But now what I want to do is I want to go through the formal sketching process. Let's take a peek. What you see on the screen now would be what I would describe as a 3-step sketching process. As I said, this is not the method for sketching. It might not always be the best method to sketch. It is a method to sketch. And it's a pretty easy one. It's very functional. And it gives us a quick picture that satisfies what we need for a formal sketch. So let's take a look at this process. It's a bit of an algorithm. Step 1, plot the vertex. We should be able to read the vertex from our equation. The vertex is the most important point on our parabola. It's our change of direction. Let's plot where we think it would lie. Now, what you see in red is a little bit of a descriptor, a little add-on, something to help you with. I put in red that I want you to label that vertex based on the direction of opening. I'll show you what I'm talking about as we move forward. Step 2, find the y-intercept. Most often, the y-intercept is going to be your easiest point to find because your y-intercept means your x value is 0. Subbing in 0 and calculating is pretty quick. That's not always the case. So what you see in red is sometimes we use a smart point. That smart point, and I call it a smart one, because you're picking what x value you want to use with a purpose. Don't just randomly pick an x value. Pick one that's going to make your life easier. That's why I call it smart. And step 3, Since you know that a key property of a parabola is an axis of symmetry, reflect the point you found across the axis of symmetry, and that now gives you a point on both sides of your vertex, specifically points across from each other. That's going to allow you to connect those 3 points with a smooth curve, and you have your sketch. Okay, there is our step-by-step process. I'm going to just very quickly do something on the bottom. This is not necessarily representative, but I want you to get an idea without the numbers getting in the way of what that process would look like. So if I put down a quick set of axes, and I was able to read my equation and it said that I had a vertex. Let's just say my vertex was down in quadrant 3. If I noticed that my parabola was opening up, then I'm going to label the coordinates of that vertex below. Again, I'll talk why. Now what I can do is I can find the y-intercept, say it's there, reflect that point, equidistant on the other side, connect them with a smooth curve, and there is a decent sketch of my parabola. Of course, all the details on that parabola would have to be labeled. But that's what I'm talking about with our process. Okay, let's jump in and actually do some sketching. Okay, for problem 2, here's our instruction for the day. Sketch. And you can see the equation. It's the exact same equation that I gave you when we described the transformations. Okay, what I want to do is I want to follow that 3-step algorithm to be able to go through and produce our sketch. Okay, so let's take a look. Step 1 says plot the vertex. Well, when I take a look at my equation, I should be able to recognize my vertex. My vertex is found by my shifts. So I can see there is the x-coordinate of my vertex. There is the y-coordinate of my vertex. Because I'm shifting my parabola to the right 3, I know that my vertex has an x value of 3, shifting it down 4, y value of -4. There is my vertex. So what I can do, plot it. I'm going to estimate on my set of axes where 3, -4 is. Now, I'm not actually going to plot it right now, and I want to show you an issue that could arise. But let's say that I did. 3, go to the right 3, go down 4, and maybe I do something like that. Okay, I had the ability to erase this easily. So if you want to follow along right now as opposed to actually sketching it on your page, that's an okay thing to do. I said that I want to label that based on my direction of opening. What that means then is, since I see that my parabola is opening up because of a positive a value, I now know I can label it below. The reason why I do that is so that I know when I sketch my parabola, it should never, ever, ever go through my label. Let me give you an example of some mistake that could happen. Okay, here we go. Step 2 says find the y-intercept. So I'm going to find my y-intercept by subbing in an x value of 0. When I do that, I now get y equals 2 times -3 squared minus 4. Okay, -3 squared is a -9 times 2 is a -18. There's my -22. I found my y-intercept. Now, if you're looking at that going, Gray, you made a mistake. Yes, I'm aware. But you won't always be aware. And so I want to show you how my label helps me. If I now went to go and plot -22 on my y-axis, it would have to be down here somewhere. What that means then is if I was to connect my vertex to my y-intercept, notice I just drew my curve through my label. I know I'm wrong. I know I'm wrong. And I found that out because I drew the curve through the label. Notice my direction of opening was supposed to be up. I clearly made a mistake. So then you go back, you find your mistake, and you go, oh, shoot, that wasn't supposed to be negative 18 because negative 3 squared, oh, shoot, that's positive 9. There's my mistake. I find that by how I label my vertex. So just a little piece of advice for you moving forward. Okay, let me get rid of that. Let me get rid of that. And we'll kind of backtrack a little bit. The second part, and I'm going to go and put my vertex back on again. There's my 3, negative 4. When I have my vertex there, and I now make my calculation on my y-intercept, that's a 2 times 9, that's an 18, that's 14. You'll also notice something that pops up. I mentioned earlier that I wouldn't actually plot my vertex, and you can maybe see why. If I were now to go and put my vertex on my grid, well, 14 would have to be way up here. That's the maximum position my set of axes allow me to use. Do not put that point off your set of axes. It's a sketch. Everyone's sketch should fit on the set of axes because you're picking the scales. So I want to highlight something when you sketch. Notice this was 4 units down, but only a little bit more was 14 units up. Your graph or your sketch is nowhere near proportional. I'm not asking you to take out a ruler. That's not the purpose of a sketch. But rather, try to make it as proportional as you can. So now, I want to show you what I would actually do. If I were you, find your vertex. Do the blue. Now go and find your y-intercept. There's the green. Now I have an idea of how far down and how far up my sketch has to include. I got an idea of my y-axis. So rather than me counting across 3 and way down here for 4, what I'm going to do is I'm going to put my vertex in a position that allows me to put 14 on my sketch, on my set of axes, in a somewhat proportional way. I want you to notice I didn't take out a ruler and I didn't do tick marks counting up. But for me to take a look at that sketch and say, well, that's about 4, that's about 14, hey, that's reasonable. By finding both of those pieces of information before I create my picture, that helps me. Okay, step 3, reflect that point across. We should be good to see that 3 units gets me to my vertex. That's also my axis of symmetry. So if I reflect that the same distance to the other side, then that's going to get me my 3rd point. So what I do is mark my point across. Now I need to label it. Well, that means I have to travel 3 and another 3, so that's 6. I'm going directly across, so I have the same y-coordinate at 14. I now have my 3 points on my parabola. That means I got an idea of shape and location. The only thing left to do, connect them with a smooth curve. And so bring that down, smooth curve at the vertex as best as possible. Oh my goodness, I just missed my point. Oh. Well, the nice thing about a sketch, I'll make my little point just a little bit bigger, and there we go. Okay, be very sure, very focused that you don't, in order to get through points, Make your parabola wrap back around because now that wouldn't pass the vertical line test. It's not a function. Make sure it's not a V. And there we go. Okay, there is your sketch. And that is how we can use that algorithm to get there. I think that walkthrough on the first one gives you enough to really be trying these next ones on your own. Okay, let's take a look at B. Okay, I think you should be able to start this one and we'll come back in the end and see how we match up. So pause the video now. Okay, we're back. So I take a peek. First thing I look for is my vertex, and I should be good. My vertex has to be at -2, -3. Shift it to the left 2, down 3. Okay, now I need my y-intercept. So to find my y-intercept, that means my x value is 0. That gives me this. We should be pretty good to calculate that quickly, and we come up with a y-intercept at -7. Now that I see I have to go to -3 on my y-axis and -7, I think -2, -3 is maybe a good spot to put there, and then a y-intercept at -7 has to be a little more than double the way. Okay, I'm going to label my vertex based on my direction of opening, and I see that it is opening down. So, -2, -3, there is my vertex. I get a little confirmation that I am going through, and when I connect that, I am not writing through my vertex, so I'm good. The only thing left to do, reflect it across my axis of symmetry. That will give me an x value of -4 and the same y value. Smooth curve. Make sure you pass the vertical line test, and you are good. So, how did we do? Hopefully not too bad. And even though we've only done 2 sketches, I'm hoping that I have a bunch of you that are starting to feel comfortable with that process. Okay, let's keep it going and try another. Okay, you see the equation for question C. I want you to give it a shot. Pause the video now. Okay, we're back. So, same process. Vertex should have been found at -3, 4. You notice your direction of opening is down. Okay, now you are finding your y-intercept, which means your x value is 0. That means when I go ahead and I sub in, I'm going to get 3 squared. Okay, there are 2 things that come into play, and some of you may be kind of thinking about it a little bit. Well, back when you gave me the algorithm, you might say, you said use the y-intercept or a smart point. And I still haven't seen what you mean by a smart point. Okay, here's where I'm going to show you what I mean about a smart point. I want you to take a look at how my green is going to simplify. When I work my way through right now, I have to square my 3. And some of you, when you took a look at this original equation, you probably went, ugh, look at what I circled in red. Look at your A value. Ugh, it's a fraction. I don't want to work with fractions. We should be fine to work with fractions. It doesn't mean that you should seek out opportunities to. But I want you to notice what happens in green. My operation of 2/3 times 9, it cross-reduces. And so pretty quickly, that thing cleans up. And you look, you never really had to work with fractions. Because it cross-reduced, that was really, really nice. Now you get that value of -2, you're good, that's an integer. And you're good to go. Okay, what I want to do is I want to show you what could have happened if that didn't happen. Like the work that we would have had to do if it did not cross-reduce. In order to do that, I'm going to go back to my original equation and I'm going to change it. I don't want you to. I just want you to watch and follow along. But I'm going to change my equation. And just for the sake of it, I'm going to make my denominator a 5. Okay, I just want to make it something different. I want you to see what would happen if I did the green again. I'm just going to do it in orange to match the color in the equation. If I said that I want to find my y-intercept, which means x equals 0, everything stays the same. But right at that moment, notice, you don't cross-reduce. Like, when I calculate that, 5 does not share any common factors with 9, let alone itself. So my fractions don't disappear. Now, we should be more than capable with that. Negative 18/5. But now you're stuck getting a common denominator. Okay, that was a total fluke that we got back to the same sort of a value. I know it's positive, but we get back to 2/5. Look, you have more work to do. Like, you got to find common denominators. You got to multiply fractions. Ugh. As I said, we should be good with what I just circled. But I think we would like it if it looked like the green. So, what am I talking about when I say a smart point? Well, this is one instance of what a smart point could look like. I said find the y-intercept or a smart point. So you don't have to do that. You don't have to find the y-intercept. Instead, what if I said this, that I was just going to sub in a different x value? Look back up in your equation. Because that denominator was 5, subbing in 0 didn't help. Can I now get you to look at the green solution? Notice my fractions cross-reduced because the number on the inside of that bracket had the denominator's factor in it. That way, you can see it in the red and green, I could divide out a common factor of 3. So, my goal might be, if I'm going to find a smart point, I want, look back up into your original equation, what I just boxed in to give me a 5. That's what I want, because then it will cross-reduce. So I could say to myself, well, what number could I replace x with that makes the inside of those brackets a 5? And hopefully pretty quickly, you come in on a value of 2. Okay, let's see it play out. Well, then that means that I have a negative 2/5 times a 2 plus 3, which is 5. That means... And you love that because now that cross reduces. And pretty quickly, you get to work with integers again. So what you see in purple is what we would refer to as a smart point. It was a point that was really easy to work with. It was smart because you didn't just randomly pick an x value, you picked an x value with a purpose. So, in case you were questioning, smart point, there's an instance. Okay, I'm going to get rid of all of that stuff now because that isn't any part of this problem. And if we go back, now we should be good with our picture. You see on your y-axis, you have to get up to 4 and down to negative 2. So if I plotted my negative 3, 4, somewhere up here, I'm opening down, so I label above. My y-intercept is at -2, so about half that distance. I can reflect that across. My vertex is at -3, so I had to go 3 and another 3. That gets me out to -6. I'm directly across, same y. Now connect them with a smooth curve. And there we go. Okay, hopefully we matched up on C and you gained some insight from that discussion about smart points. Okay, one last problem for today. Okay, I want you to work your way through D. I'd like you to go through, provide a sketch for the equation in D. Pause the video now. Okay, we're back. So I am hoping that we were pretty quick to be able to say vertex was at 0, -5. However, I may have had some people who got jammed on that one. If we had a problem finding the vertex, I just want you to keep in mind that my equation could have looked like this. For anybody that needed a value inside the brackets to find your vertex, okay, there's your red. But I would hope that we could have just looked at that equation and said, vertical stretch by a factor of 2, it was not shifted horizontally. So the x-coordinate of my vertex is still at 0. The only thing that happened was a shift down 5 afterwards. So we could have had a bit of a snag going through and finding the vertex. Okay, hopefully we've got that. We're good. Now you need to find your y-intercept. Well, I am telling you, you really have the blinders on. If you went y-intercept means x equals 0, look above in blue. And then you went y equals 2 times 0 squared, 2 times 0, only to go, oh, yeah, we already knew that. Okay, make sure we don't have the blinders on. Yes, it is an algorithm we're going through, but that doesn't mean we stop thinking. Okay, I mentioned before that we had one instance of a smart point. Maybe you'll notice, here's another instance where we need one. Because what you just found was your vertex at 0, -5, I'm just putting it there for the sake of argument. Finding the y-intercept is going to give you the same point. We don't have 3 points on our parabola, and that's what we need to see the shape. So that means that you need to find 2 other points. So what we need to do, find a smart point. Now, there is no fraction that comes into play here, so this shouldn't be a matter of the types of numbers we're working with. Rather, this is about distance. Some people would be tempted to say, well, then I'm just going to pick like the easiest x value to sub in. I can't sub in 0, so I'm going to sub in 1. And now when you sub in 1, you get 2 times 1. There's your -3. I just want to show you something. And this is about accuracy of sketch. If you put that as your vertex, you then say 1, -3, reflect it. Because those 3 points are so close together, maybe you connect it like this. But could you also see? That would be reasonable. We start to get different shapes because the points are so close together. That there is something to having our points be farther apart. Now, it doesn't mean that I want to go and I want to sub in an x value of 10. Like, I don't need them to be that far apart. However, a couple units is usually sufficient. So, my advice to you, it doesn't have to be followed. This is advice. Pick an x value that's at least a couple units away. That'll give you a little more distance between your 3 points, which will make our sketch more accurate. So I would pick an x value of 2. That's going to give me 2 times 4. That's an 8 minus 5. There's my 3. So now I can see I have to get down to -5. I don't label the 0 in that because it's a y-intercept. Just label the value. Now, when I put 2, 3 on my graph, my points are far enough apart. This is going to actually create a pretty accurate sketch. Reflect that across. And now when I connect those with a smooth curve, come around, make sure I pass the vertical line test. It's really hard to not draw these parabolas like they're lines on both sides, but there we go. That's the other instance of a smart point. Just trying to get our points far enough apart to provide accuracy. Okay, there is our one method for going through and sketching. The idea of plotting the vertex, finding a point, reflecting in the axis of symmetry. I mentioned to you at the very beginning of the video that I was going to sneak another method in. This is a method that's often referred to as the step method. And what it really uses is transformations. And in particular, it uses our a value. If you look back up at our equation, it uses the fact that our a value is 2, the part that determines the shape, to create our parabola. So what I want to do is I just want to sneak in an alternate method for sketching right now. I think it could give us a more well-rounded approach. I want you to imagine that I do not have the red parabola there. Okay, I don't have it. All I have is my blue point. So what I'm going to do is I'm going to actually erase that red parabola. I want to keep the purple there just so you have an idea, so you can see that these things do line up. But what I want to do is I want to talk a little bit about how we can get other points other than just using substitution, picking an x value, subbing it in. What the step method does is it defines the shape. It actually says, you know the shape of that parabola, so find your points. Okay, what does that mean? Well, if I shrink this down a little bit and I put on a quick sketch of what our usual parabola looks like. Down in the bottom, here's my set of axes. Here is my standard parabola. If you recall, we have this certain pattern with our points. And I'm going to really zoom in. That when I look at that parabola, I know that for me to go from my vertex to 1, 1, I went across 1 and up 1. But then for me to go to my next point, which was up here at 2, 4, I go across 1 again, but now I go up 3. If you want to think about that as steps. Over 1, up a bit, over 1, up more. Specifically, over 1, up 1, over 1, up 3. Okay, in orange, if we have a shape that was created by a vertical stretch of a factor of 2, then what that means is this 1 that I went up, I don't go up 1 anymore. I go up 2. This 3 that I went up, I don't go up 3 anymore. I have to go up double. I go up 6. That would define my new shape. So if I got rid of that, and I just went and put back in my purple, my base parabola goes to the right 1 and up 1. then right 1, up 3. My new parabola in orange goes to the right 1, up 2, and then we'll go to the right 1, up 6. There is my new shape. And I can just use my shape to find the location of other points. So let me come down out of that picture. If I look back at the parabola I was given, I can read my vertex directly from my equation. Well, now I need to get 2 other points on my parabola. Well, I can use the step method. Because of my a value of 2, if I go to the right 1, I go up 2. That would give me a point in that location. That point, and I'm going to label the coordinates, would be at 1, up 2 from -5 gets me to -3. That point is really big. Let me just get rid of that. There's a reasonable point. Actually, I don't even like that point. It's a little too far to the right. There we go. That would be about 1 unit. Well, now for me to get my next point, I go to the right 1 from there, and now up 6. And if I go to the right 1, I'm at an x value of 2, and if I go up 6 from -3, I now have a y value of 3. You'll notice you come in on the same purple point. So I could use the step method to then get those 2 labeled points. Of course, I can reflect them, but it wouldn't require any points being labeled on the left side. Ooh, wow, that is a really bad shape. Because I have my 2 points on the right with my vertex. Okay, that's an example of your step method. And some people really like that. So I found a way to sneak in an alternate method in the end. Okay, your job for today. Get really, really good at being able to follow that algorithm of plotting a vertex, finding a point, reflecting it. If you're looking for a little variety, especially when a smart point is required, then maybe consider practicing your step method. Give that one a shot. It really helps to kind of hunker down the idea of shape. Okay, your job. Jump in. Get lots of practice. Best of luck.